Works? Okay, so quick announcement. A lot of you have taken your posters down already. So just to let you know, there's actually a prize for best poster. So if you want that prize, you need to put your poster up. So if you've taken your poster down, please go put it back up before the next coffee break if possible. Thank you.
Okay, we can start. Welcome to the afternoon session. We'll have Shlomo Razamat talking about news from the higher dimensional quantum field theory frontier. Please.
So first I would like to thank the organizers for giving me the opportunity to present this talk. So I will be overviewing certain understanding or progress in our understanding of higher dimensional supersymmetric quantum field theory. So it's a huge subject. I will take a certain slice through the subject, review certain aspects in more detail, and others I will touch upon as we go. So throughout this talk, we will be interested in supersymmetric quantum field theory. So this will be usual vanilla unitary Poincare invariant in flat space and at least minimally supersymmetric quantum field theories. To be more precise, I will be interested in understanding supersymmetric conformal field theory, so endpoints of renormalization group flows. And we will study deformations of these endpoints, and all the deformations that we will study will also preserve some amount of supersymmetry. I will not say it again, but everything I will be talking about will be at least somewhat supersymmetric. Okay, a typical textbook discussion of quantum field theory starts by choice of space-time dimension, and it also appeared in the title of this talk. And throughout of this talk, the dimensionality of space-time will be denoted by this calligraphic D. So the talk is about higher dimensional SQFTs, and the reason is that if we want to discuss interesting superconformal field theories, we are restricted to dimensions equal or smaller to 6. And quantum field theories in different numbers of dimensions behave qualitatively different. So in dimensions bigger than 4, we don't have Lagrangian descriptions of these theories which flow to interacting theories. In dimension equal to 4, we have quite a variety of such descriptions, and in some sense, in dimensions lower than 4, there is a huge plethora of such descriptions. So we will focus in this talk on this dimensionality, equal or bigger than 4. I will say something about dimensions smaller than 4, and as we will see, the whole philosophy of this talk is that we should not separate quantum field theories according to their dimensions, but again, the main focus will be on these dimensionalities. So there are various ways in which we can construct supersymmetric conformal field theories. One I already mentioned, and this is purely field theoretic. We start from a Lagrangian, from fields and interactions, and this we can do in dimensions equal or smaller than 4 if we are interested in interacting theories. We can have stringy constructions. We can embed the whole discussion in this larger setup of string theory and construct the quantum field theories of interest in string theory, some limits of string theory. And of course, once we have constructed something stringy, we can do something hybrid. For example, we can take a theory, existence of which we deduce from string theory, and do to it quantum field theoretic things, such as gauge symmetries and perform various deformations. So, type of questions that I will want to review or touch upon are depicted in this Venn diagram. So what we will want to do is to understand how the space of all SCFTs looks like. So part of this space is this red circle is given by free field theories and deformations of these. Okay, irrelevant deformations of this. Another part of this space is constructions which one can obtain starting from string theory. And what we want to understand, what are the relative sizes of these circles in these Venn diagrams. For example, is it really that this circle is smaller than the space of all SCFTs? Maybe it's, in some sense it covers the space of all SCFTs. Are there things that we cannot engineer neither using Lagrangians nor using string theory and so on? Okay. On the previous slide, we had these Venn diagrams of circles. So now let me say a couple of words how we populate these circles. So we define quantum field theories. Ultimately, what we would want to do is to define these supersymmetric conformal field theories. Okay. In this way. by specifying the spectrum of all of the operators and all of the correlation functions, but typically this is not something we can operationally do. So we define things through some skeletal information, some symmetries, anomalies, BPS spectrum, moduli spaces, and so on. This does not capture the full information about these animals, these theories, but it captures some essential information. And typically by defining the theory, that's what I would mean, defining some skeletal information. Now, the way we call theories, we name theories, is by various constructions we have for them. So Lagrangian or stringy, and all of these names actually refer to these types of constructions, either directly to a construction or to names of people who constructed actually these theories. And throughout this talk, we will use these mnemonic notations where the D-gons will represent theories, superconformal quantum field theories in D dimensions. And luckily, we don't go below 3 in this talk. And to be even more precise than the previous circle, what I will focus on in this talk is not on defining any particular theory, but rather studying interrelations between different quantum field theories in various dimensions. So given a theory, it might have different types of constructions. It can be renormalization group, fixed flow, starting from different UV starting point. We can engineer a theory in string theory. There is a variety of things we can do, and also given an SCFT, we can obtain from it some other SCFT, and so on. So what we will try to do is to map or understand a little bit better this space of different theories. So there is a lot of progress on these types of questions in over the last 30 years or so, and I roughly divide this progress into 3 parts. So first of all, we would want to know what are the SCFTs that are there, to enumerate all the SCFTs in dimensions equal or smaller than 6. Then there is a progress on understanding what is the skeletal information, what is the information we can associate to every theory we find, and what is even in principle the skeletal information that one can compute, and then the structure of the theory space, the various relations between different quantum field theories. So I will focus on this part of this progress, and I will touch upon a little bit on other points as we go on. So the progress in recent years that has been achieved was mainly due to understanding these relations between supersymmetric quantum field theories, either in a given number of dimensions or across different dimensions. And this will be our focus. And something which will be a little bit left behind the scene is the relations that one can derive from string theory. But again, this is a very important part of the progress, which I will mention in passing. So this will be the plan of our talk. I will have a very short executive summary of what one can do starting from string theory, and then we will review various aspects of relations between SQFTs between themselves without referring directly to string theory. So we will first start by discussing some relations between SQFTs in a given number of dimensions. Then we will discuss what can be deduced about SQFTs in lower number of dimensions from SQFTs in higher number of dimensions. And finally, I will comment very briefly on what might one possibly deduce about SQFTs in higher dimensions starting from lower dimensions. So let me just flash this very brief slide about string theory. So there is a variety of techniques using which one can construct supersymmetric quantum field theories in string theory. They are listed here. And the important fact is that using these types of techniques, we can argue for existence of certain quantum field theories, non-trivial interacting quantum field theories in 6 dimensions and say in 5 dimensions. There is a conjecture classification of all D equals 6 SCFTs, and there is also a lot of attempt in classifying 5-dimensional SCFTs. One can do many things in 4 dimensions, but there is no claim about a classification of what one can do directly in 4 dimensions using these techniques. Okay, so again, I will just flash it very briefly, and we will mention these various facts as we go. So now let me start with the main part of the talk and discuss what one can deduce about SQFTs, starting with SQFTs and fixing the number of dimensions. Okay. So we will organize things with how we construct the various theories. So throughout this talk, the different shapes will represent dimensionality, weird shapes will represent undefined dimensionality, and red shapes will represent Lagrangians. Okay, so anytime you see red, there is a Lagrangian. So in dimensions smaller or equal to 4, we can start from free fields and engineer interacting interesting quantum field theories. These renormalization group flows do not have to end in an interacting SCFT. They might end in a gap theory or a free theory, but at least in principle, we can engineer interacting SCFTs. In dimensions smaller or equal than 5, including 4, of course, we can start from these interacting SCFTs and continue performing various field theoretic operations to engineer interesting quantum field theories. And in some cases, also we can obtain weakly coupled Lagrangian theories. And this is, for example, very interesting in 5 dimensions, where we can relate strongly coupled 5-dimensional CFTs in this way to weakly coupled gauge theories in the infrared. Another thing that we can do in any number of dimensions, we can explore the moduli spaces of vacuum. Okay, we can turn on vacuum expectation values and ask how the theory looks like on a generic point of the moduli space. So let me start overviewing or briefly reviewing and commenting of the progress related to this exploration of moduli spaces. So most of the progress is achieved with theories with 8 supercharges, where we have this clean distinction between 2 types of branches of vacua. And of course, it's an old subject of trying to understand and even classify, for example, theories in 6 dimensions by exploring the physics on the tensor branch or the physics of the Coulomb branch in 4 dimensions, and the progress in this field is ongoing. And if you're interested, here is a nice review article on this subject. What happened in recent years that not only we learned something about this Coulomb and the tensor branches that are in a sense simpler, there is a conjectured prescription to try and understand how the Higgs branches of various theories look like. And the way this prescription goes is by associating a certain 3-dimensional auxiliary object, which is usually called a magnetic quiver, and studying the Coulomb branch of this magnetic quiver, one can deduce physics of the Higgs branch of various theories with 8 supercharges in various dimensions. So the basic idea going into this magnetic quiver story is the idea of mirror symmetry, although it is not equivalent to it. And once we go to 3 dimensions, the structure of these Higgs branches and Coulomb branches becomes more restricted, and the 2 branches appear more symmetrically. Again, and this leads to this idea of mirror symmetry. Now, another part of the progress is understanding the moduli spaces of theories with more supersymmetries, say n equals 4 and n equals 3 supersymmetries, where the moduli spaces are typically, if one ignores various discrete gaugings, has this type of structure, and there is a lot of work understanding this. Now, 2 comments I want to make here about open problems, which I find very interesting. So although with n equal 2 supersymmetry in 4 dimensions, there is this naively clean distinction between the 2 branches, the Coulomb branch and the Higgs branch, there are tantalizing hints that these 2 objects are in fact related. And this goes through this subject of vertex operator algebra, which are very Higgsy objects, although they are not exactly Higgs branch objects. And certain computations here one can perform also on a Coulomb branch by counting certain BPS particles and obtain the same result. Okay? And so there is something to be discovered there. Another very intriguing relation that I want to mention, which will be also discussed in a talk by Sarah Pasquetti, is that this mirror symmetry that we all know and love in 3 dimensions can actually be lifted in a particular way to certain duality properties of 4-dimensional n equal 1 theories in a surprising way. So after I mentioned this notion of duality, let me go to this slide of relations between SQFTs, following this idea of duality. So what is duality? There are 2 types of dualities. There are actually more than 2 types of duality as is written here, but first type of duality is as follows. You start from 2 different quantum field theories, deform them in different way, and you obtain the same physics in the infrared. So in the infrared, if NRG flow is involved, but this duality duality can also be completely conformal with no renormalization group flow involved. Another type of duality is sometimes called UV duality, where you start from a given SCFT and deform it in two different ways, okay? And obtain two different SCFTs. So this is a funny thing to call duality, but again, it becomes very useful, for example, when one studies 5 dimensions, when one knows very little about the starting fixed point, and one might be able to deduce various bits of information about it from the infrared physics obtained in this way. And finally, one can obtain the same SCFT by renormalization group flow, starting with some superpotential and gauging deformations, or by exploring moduli spaces of other theories. So let me give several examples and make several comments. So here is an example of a 5-dimensional UV duality where you have a UV SCFT in 5 dimensions. You perform different deformations, different basically mass deformations of this theory. And in the infrared, you obtain a nice gauge theory description. So these gauge theories are infrared free, and they capture some of the information of this 5-dimensional quantum field theory. And of course, there is a huge plethora of examples of IR dualities in 4 dimensions with minimal supersymmetry when one starts with the work of Seiberg almost 30 years ago. So you have 2 Lagrangian theories which are deformed, and one obtains the same SCFT in the infrared. With n equals 2 and n equals 4 supersymmetry, there are many examples of conformal dualities where you have 2 different weakly coupled Lagrangian theories which reside on the same conformal manifold. Okay, so any point of this, different points of this conformal manifold can be accessed in principle by these 2 different descriptions. And also an interesting fact which goes back again almost 30 years is that there is actually a huge variety of n equal 1 conformal manifolds in 4 dimensions. And an interesting open question is whether there are interesting examples of dualities with only n equal 1 supersymmetry as duality. So here is an example. You have a G2 SQCD with some matter content and some quiver theory with some matter content. If you compute the skeletal information that I mentioned before of these 2 theories, you obtain exactly the same thing. So this is a conjecturally dual pair of theories. So these are 2 weird theories, so you can fear that there are not too many such examples, but in fact there are a huge number of gauge theories that you can write down which have non-trivial conformal manifolds. And there is this interesting question: what is the S-duality structure of this conformal manifold? Is there at all an S-duality structure? What is the geometry of this conformal manifold of theories with n equal 1 supersymmetry? Now, in previous slides, I discussed theories which, all the theories that we discussed had Lagrangians, and they flown to some interacting fixed points. There are other types of theories that we can engineer, starting from string theory, as I mentioned before. So an example, or a beautiful example of such a construction is a construction of purely n equals 3 supersymmetric conformal field theories. So one can ask where they sit in all of this picture. So interestingly enough, you can engineer at least some of these theories, again, starting from a Lagrangian theory, which manifests less supersymmetry. It's only n equal 1 supersymmetric. You deform it by relevant deformations. It flows to infrared to some fixed point, which conjecturally resides on the same conformal manifold as this n equals 3 SCFT. Okay. Again, you can check this claim by comparing various skeletal informations between the 2 constructions. So we have 2 constructions, a stringy construction and a Lagrangian construction of the same theory. And note that here the n equals 3 supersymmetry, again, conjecturally emerges on some locus of this conformal manifold. So in recent years, surprisingly, many strongly coupled SCFTs which are constructed in string theory acquire this type of Lagrangians. There's vanilla Lagrangians, but which manifest a little bit less of symmetry and sometimes a little bit less supersymmetry. So then I want to ask these existential questions. Are there really non-Lagrangian theories? So there is this notion of a non-Lagrangian theory, a theory for which at the moment currently we don't know of a known Lagrangian. So this question can be phrased for dimensions equal or smaller than 4. Can all SCFTs be constructed by deforming free fixed points in various ways? Okay, and this question can be refined in various ways. For example, given an SCFT in D equal or less than 4, the skeletal information, are there obstructions to building a Lagrangian? Even if you cannot build a Lagrangian, can you argue that this Lagrangian cannot be built? So the idea behind this question is as follows. Of course, we all know that the infrared physics is constrained by the notion of anomalies, the 't Hooft anomaly matching conditions, and these conditions are being extended and explored beyond the notion of what is now called 0-4 symmetries in many, many works. So the question is whether we can go the other way around. So given the full, say, generalized symmetries and anomalies of an SCFT, which substructure of this can in principle be engineered by free fields? Okay? And what we have in mind that the rest of the structure might only emerge in the infrared. Okay. So here are a couple of examples. So this example is a 3-dimensional example, is a simple one. So we have here an SCFT with some amount of supersymmetry, time reversal symmetry, and global symmetry. And by now we have 3 different descriptions of this SCFT, each one manifesting only part of the symmetry group of the infrared theory. So the question is whether we are not just smart enough to find a manifestly symmetric description, or there is some abstraction, or this is just some fluke without any generic lessons to be learned from. Another example I want to mention is it goes to 4 dimensions. So here we have this famous Minahan-Nemeshansky n equal to E6 SCFT, which is some strongly coupled theory with E6 global symmetry. And by now we have several descriptions, Lagrangian description of this theory. So we start with, again, vanilla Lagrangian with some gauge group. So for example, here is a spin 6 group with some matter content. And the theory manifests in the UV certain subgroup of the global symmetry in the infrared. This is 6 times U1 in n equal 1 language. But the claim is that it flows in the infrared to this famous SCFT. And here is yet another Lagrangian for the same theory. So this non-Lagrangian theory now has several Lagrangians with the symmetry that we expect in the infrared emerging in this renormalization group flow. So another question I want to pose related to this issue of emergence of symmetry in the infrared. Of course, it's not a new effect, but there are many interesting examples of this about which we now learned. And the question is as follows. Given that some symmetry emerges in the infrared, what we can do, we can get to this infrared fixed point and then couple this emergent global symmetry to dynamical vector fields. We can gauge that symmetry. And the question is whether a theory is accessible by renormalization group flow starting from Lagrangian theories are the same as one can arrive to by these types of constructions. So whether this set of theories is bigger than that or they are just equal. This is a funnier thing one can do, and the question is whether these two are any different or not. Okay, so this is what I wanted to say about relations or comments that I wanted to say about theories in specific dimension. And now I will start going across dimensions. I will start from higher dimensions and go to lower dimensions and make several comments. So this is the basic idea. You start from some theory in d prime dimensions, you put it on compact space, and go to low energy where your theory becomes effectively lower dimensional, say d-dimensional, and you study what you get and what type of things you can deduce from this procedure. Again, as before, the resulting theory in a lower number of dimensions can be either gapped, free, or interacting as SQFT. By definition, the theory in lower dimensions that you obtain is UV completed using the higher dimensional description. And the question is whether this is a UV complete theory by itself in these lower numbers of dimensions. Now, a claim to fame, not the claim to fame, but a claim to fame of these types of constructions, that one can actually predict the existence of a lot of lower dimensional theories starting from higher dimensional ones. As I mentioned, we know about higher dimensional theories because we can engineer them, for example, in string theory. So in this way, we go from string theory through 6 dimensions to lower dimensions and can predict a lot of theories and try to ask various questions about these theories. So let me start with more concrete questions and examples by going from 6 dimensions to 5 dimensions. So in some cases, starting with a theory in 6 dimensions and putting it on a circle with various background gauge fields, holonomies, one can obtain an effective theory in 5 dimensions. In some cases, starting with a theory in 6 dimensions and placing on a circle, the effective theory in 5 dimensions turns out to be a gauge theory. So there is this string theoretic construction, in a sense, of this 5-dimensional theory. You start in 6 dimensions with a theory, place it on a circle, and you get something in 5 dimensions. On the other hand, you have a completely Lagrangian theory in 5 dimensions. So in a sense, one can think of this situation as a duality across dimensions. You have 2 descriptions of the same theory. This theory turns out to be simple in this case. So a question that one can ask is as follows. For example, which 5-dimensional gauge theories are across dimensions dual to compactifications of 6-dimensional theories? And this question can be refined and rephrased in various ways. For example, which 5-dimensional gauge theories are UV completed by 6-dimensional SCFTs, and which are deformations of 5-dimensional SCFTs? So here is a deformation of 5D SCFT, here is compactification of a 6D SCFTs. And in fact, starting from the same 6D SCFT and performing different deformation, we sometimes can arrive at different 5-dimensional gauge theories. And finally, another question which one can phrase is whether all 5-dimensional CFTs can be obtained by circle compactifications of 6-dimensional CFTs with various parameters turned on upon compactification. And here is just a very small snapshot into the literature on this subject. So these types of questions are very vigorously investigated in recent years. Now, when one goes farther down, not to 5 dimensions, but to 4 dimensions, one can do many more things. And the new things, the new kind of thing that one obtains by going to 4 dimensions is that we can actually engineer interacting superconformal field theories directly in 4 dimensions. So a question one can ask, does a given geometric construction of D equals 4 interacting a CFT, and by geometric I mean starting from 6D SCFT and placing it on some 2-dimensional surface. So does a given construction have an explicit construction as a deformation of a free fixed point directly in D equals 4? So again, I will call it a duality across dimensions. If such a description exists, this situation is similar to Seiberg duality inside the conformal window, where we have 2 UV complete constructions of the same SCFT in the infrared. The UV complete constructions start from different dimensionality, but the basic idea is very similar. So let me give you some examples and make some comments. So this is a famous example of Gayotto from many years already, and the claim is if you start from a 2,0 theory, the simplest interacting one, the A1 2,0 theory, and place it on a genus G Riemann surface, the theory in 4 dimensions is a cross dimensions dual to a simple gauge theory, SU2 to the power 2G minus 2 SQCD with some matter content. So again, we have two constructions. There is a construction coming from basically string theory, where we engineer the 6D SCFT and then we reduce it to 4 dimensions, and a simple gauge theory. Oh, sorry, this is the same picture. And another description directly in 4 dimensions. Okay. Yet another example, going back to the Lagrangians for E6 SCFT that I have mentioned. This can actually be used as building blocks to construct cross-dimensional duals for compactifications of any A2 2,0 theory on a Riemann surface. So you take, for example, this theory on a genus G Riemann surface, and you use the Lagrangians of the E6 n equal to Minahan-Meshansky theory, and you can construct Lagrangians for all of these compactifications. These are Lagrangians, albeit you need to gauge these emergent symmetries. Okay? So here, no emergent symmetries need to be gauged, but here, this class of theory seems to be Lagrangian, but you need to gauge these emergent symmetries. Now, the two examples on the previous slide were starting with 2,0 theories in 6 dimensions, but in this respect, nothing is special about 2,0. We can start with 1,0 theories, of which there is a huge variety, and try to understand the cross-dimensional dualities for them. And here is one example where you start with the so-called E-string theory, some SCFT in 6 dimensions, which has an E8 global symmetry. You put it on a genus G Riemann surface, and again, you obtain a very simple gauge theory, now with a different gauge group. So this is again an example of a cross-dimensional duality. And by studying these simple gauge theories, you can recover various bits of information you expect from these compactifications. For example, you can see the remnants of global symmetry, dimensions of spaces of parameters, and so on. Now, a point I want to stress is what these dualities across dimensions exactly mean. So again, we start from a 6-dimensional theory, we place it on a 2-dimensional surface, we go to 4 dimensions, and this is a definition of our 4-dimensional theory. Now, there might be this Lagrangian description of which flows exactly to the same conformal manifold, and if we tune parameters to the same fixed point, by definition, this is something which is UV completed by this 6-dimensional theory. This 4-dimensional theory might be also UV complete by itself in 4 dimensions, but things are not always very simple. For example, the theories that one can construct might have very relevant interactions of this sort. So you have some free field which couples to some operator of very high dimensions. So this is a very relevant deformation which basically disappears once we get into infrared. So one can think of these descriptions as descriptions at some intermediate scale in various examples. So this is a summary of the status of this subfield. So by now we have a lot of examples of cross-dimensional duals for compactification, starting either with 2,0 theories, and here are names of some very popular theories which are considered to be non-Lagrangian, or starting with 1,0 also, there are many situations for which we know this cross-dimensional duality. So a version of the question I asked before, which was, do all 4-dimensional CFTs have a Lagrangian, is do all 4-dimensional CFTs constructed across dimensions through these geometrical methods have explicit constructions? And since most of the theories we know exist, are constructed through string theory by these types of geometric constructions, practically these two questions are more or less equivalent. Now, let me make several further comments. So first of all, I made various claims about across dimensions dualities of various theories. So a natural question is how one at all knows or conjectures these types of things. And the reasoning is exactly the same as in the 90s about usual dualities. So what one can do, one can compute various bits and pieces of this skeletal information directly from 6 dimensions or in 4 dimensions, and perform numerous consistency checks on any claim, and that is the only way one argues for these dualities. So all of these dualities are conjectures, as any other dualities. And in this respect, it is very interesting and very important that there is this huge amount of new skeletal information that is being developed unrelated to these higher dimensional theories directly and across dimensional dualities and whatnot. And many of these things are being discussed also in this type of context. So some aspects of this, I believe, will be touched upon in the talk of Kantaro Amori, and some more string theoretic ones in the talk by Iñaki Garcia Echevarria later this week. Another brief comment I want to make is about holography. And of course, holography is an extremely strong tool to try to understand interacting SCFTs, and this is not an exception. So there are various things that people can do. Again, classify ideal solution, study generalized symmetries and anomalies from holography, and so on, and some more directly related questions to these types of things that I'm discussing here. And here is an example of a computation due to Ibrahim Abba and collaborators, where these types of interactions, which from field theory basically are derived from consistency of anomalies and other types of skeletal informations, can be also argued for, at least in certain setups, by studying these geometrical holographic realizations of these cross-dimensional dualities. Okay. So let me ask another, I think, very fundamental question, is whether there is, or one can even think about a systematic derivation of dualities across dimensions. So in the dualities that everybody is familiar with, like Seiberg dualities in 4 dimensions and so on, there is no systematics of how to predict these dualities. We know about them, we have a huge plethora of examples of these, but we don't have a systematic way to derive them in field theory. So I want to briefly mention here that an algorithm integrating a lot of things that people are discussing from various points of view in this supersymmetric world can be devised. And it goes by choosing a 6D theory, existence of which is derived from string theory. In lucky situations, there might be a 5D gauge theory description. Again, this is something which, this is a statement into which a lot of things go. And then trying to understand these 5-dimensional theories, basically boundary conditions, domain walls, boundaries, defects in these 5-dimensional theories. Again, there is a lot of discussion of these types of topics. One can really systematically derive cross-dimensional dualities of these 6D theories on a particular type of 2-dimensional geometry. And finally, integrating understandings of vacuum expectation values flows in 6 dimensions, this compactification procedure, and Web flows directly in 4 dimensions. In some cases, this can be generalized. So there is an algorithm. It's not an extremely systematic one, but there is a lot of things one can do and one can study. Another thing I want to mention is the relation between these 2 types of dualities that I have discussed. So in-dimensional dualities, like Seiberg dualities and conformal dualities that you discover in a given number of dimensions, and the cross-dimensional duality. So a very rough statement is that there is a very intimate relation between the 2, and the former, the in-dimensional dualities, are often consistency conditions on a cross-dimensional dualities. And the way it goes is as follows. So you, for example, want to understand the cross-dimensional duality starting from some 6D SQFT compactifying on some 2-dimensional surfaces. You understand this cross-dimensional duality for a variety of surfaces, and then you can perform the following operation. You can geometrically glue these surfaces together to obtain a different surface, and you might be able to do it in different way. Since you obtain the same surface, the 4-dimensional theory associated to this surface also should be the same. But you have now 2 ways to performing this operation, where gluing translates into gauging and superpotential in quantum field theories. So there are many examples of dualities, very well-known ones, which can be engineered in this way. For example, various types of Seiberg dualities, N=2S dualities, interligator-Puyo dualities, and many more. There are some dualities that can be engineered in this way, which look novel. For example, here is a simple duality, and it is a bit tricky to see how it, whether at all it can be obtained from very well-known ones. In this particular case, by complicating this theory and doing to it various things, one can actually show that it reduces from one of these dualities. But in general, we don't know whether the dualities you obtain geometrically are new or not. One can obtain a lot of dualities, and an interesting question, for example, is whether there is a basic set of 4-dimensional dualities from which everything can be derived. Okay? And again, this will be, I think, the main focus of Sarah's talk. There are other dualities that we know about in 4 dimensions, such as dualities with joint matter fields, which at the moment we don't know how to engineer in these types of constructions, and it will be interesting to derive that. And for example, the G2 SQCD conformal duality to a quiver that I mentioned in the beginning also at the moment doesn't have any sort of geometric explanation. So a question one can ask is whether all dualities in 4 dimensions have a geometric explanations or not, or there are some new facts which are directly derived from 4 dimensions and so on. Now, another notion I want to discuss is the notion of 6D infrared duality. Okay, so I mentioned that there are no interesting renormalization group flows directly in 6 dimensions. However, we can do the following thing. We can start from 2 different SCFTs, say in 6 dimensions, and place them on different geometries, and obtain a theory in lower number of dimensions. And here on this slide, I go to 4 dimensions. Okay, so if this exists, this is exactly the situation of IR duality. You start from 2 different theories, and you get something, you have an equivalent theory in the infrared. And here is a particular example where you start either with something which is called a minimal SU3 SCFT, put it on a 4-punctured sphere, and obtain a cross-dimensional dual in terms of a Lagrangian, or you start from a strict theory on a genus 2 surface and obtain the same theory. So a question here is as follows, and there are also numerous examples of these types of dualities appearing in the literature. So the question is as follows. In the two previous slides, the philosophy was that lower dimensional dualities are explained by higher dimensional constructions. So a question one can ask whether one can explain these types of 6 dualities by something. And the natural place to look for such an explanation in this case will be going to string theory. Okay, this is already the top level. We are in 6 dimensions. So a way to look for explanations or derivations of these types of dualities will be in 6 dimensions. So this is yet another open question that one can discuss. So let me summarize various classification questions that I have mentioned. So one question is for whether starting from 6-dimensional theories and compactifying them down to 4 dimensions, down to 5 dimensions, one can obtain this full bag of theories in 6 and 5 dimensions. Whether starting from 4-dimensional Lagrangian theories, one can obtain all SCFTs in 4 dimensions. And whether both of these things hold, and further, if one goes to lower dimensions, say 3 and 2 dimensions, whether all supersymmetric physics can be derived by starting from 6D SCFTs. Now I want to mention that this question is highly non-trivial, even if one constrains themselves to the relatively well-understood world of 4-dimensional n=2 SCFTs. As was shown, for example, in these papers, there are various theories in 4 dimensions, Lagrangian theories, that one can write, about which we don't know whether there is a string theoretic or this compactification construction from which they can be derived. Okay, so the last thing I want to discuss, so we discussed the relations between QFTs in dimensions, what can be deduced about lower dimensional SQFTs from higher dimensional ones, and now I will make some comments about what can be in principle deduced about higher dimensional SQFTs starting from lower dimensional ones. And here I will first go to this topic of supersymmetric partition functions. So given a Lagrangian in any number of dimensions, there is a variety of supersymmetric partition functions which can be computed using localizations. These computations are typically directly or indirectly related to various counting problems. And as such, roughly because of that, these partition functions are usually independent of continuous parameters of renormalization group flow, and thus one can deduce a lot of information about a strongly coupled fixed point from these Lagrangian descriptions. So there are various ways in which these partition functions can be used. So here let me highlight 2 ones on this slide. So for example, if you start from a 6-dimensional theory and place it on this type of space, a 4-dimensional space times a 2-dimensional space. So one thing that one can do without understanding what a 4-dimensional theory is in this compactification, one can try to deduce properties of this resulting theory one obtains in 4 dimensions, theory denoted here. In particular, what are the partition functions on this manifold that appears in this geometry. And this is the basic idea behind this famous Aldai-Gayoto-Tachikawa correspondence and many other correspondences. And this basic idea also featured in yesterday's talk by Nathalie Paquette. There is, however, another thing that one can do. Again, in the same setup, say we now do know a cross-dimensional dual of this compactification. So we have a Lagrangian in 4 dimensions, resulting in this type of compactification. So we have a direct way to compute this partition function. And it might be that we know this compactification, this across dimensions duality for a huge variety of compactification geometry and manifolds for which we compute this partition function. So an interesting question that one can ask is whether what can we deduce about the 6-dimensional theories studying this partition function. So from these cross-dimensional dualities, we basically are computing a partition function of a 6-dimensional theory. So scanning over all of these possibilities, we might be able to deduce something interesting. And here, let me briefly mention other types of things that one can do with these supersymmetric partition functions. For example, these partition functions are typically given in terms of some very well-defined interesting special functions and various physical properties of this of the quantum field theories of interest are encoded in precise mathematical properties of these integrals and sums of these special functions. So one can do two things. One can either look on these computations of partition functions, conjecture various physical properties and see whether these mathematical objects satisfy these properties. So there is a rather big industry starting with the work of Dolan and Osborne performing that, or conversely one can start from some mathematical result regarding these types of special functions and try to deduce physics about them. For example, some old example of a lot of 3-dimensional dualities which were deduced from a mathematical thesis of a person who I'm sure didn't know much about quantum field theories, but his thesis led to a lot of physical results. Here is an example of a math paper which led to a cross-dimensional duality recently, and there are other very interesting works. For example, when one studies the partition function, sees that they have certain very, very surprising mathematical structure, and it is not clear what the physics of it is. So here I mentioned just some topics in which this supersymmetric partition function appear. For example, there are interesting questions about modularity. There is a very intimate parallel between, in a sense, classification of integrable models in quantum mechanical integrable models and classification of 6-dimensional SQFTs. There is, of course, a lot of interest in understanding this partition function since they can teach us about counting of microstates in gravity and holography. This will be reviewed in detail in the talk by Francesco Benini. So this was one way in which we could learn about higher dimensional theories from lower dimensional ones. And here let me mention yet another one. And this is also the topic with which Clay ended his review talk on a similar subject 4 years ago. But I will try to phrase it in this a little bit more modern language of cross-dimensional dualities. So the claim is like that. You can start from a 2,0 theory, some 2,0 theory, an minus 1 2,0 theory in 6 dimensions, and it is a known fact that a cross-dimensional dual for this theory exists. If you put it on a Riemann surface, on a torus with certain types of defects, certain types of punctures, you obtain a vanilla quiver theory. Now, a conjecture of the construction, a very old one, is that if you take this theory, you take a large number of punctures. This is one limit you take, and another you study certain vacuum expectation value deformations which geometrically correspond to basically erasing these punctures. So you take this double scaling limit of taking a lot of punctures and removing them. The claim, the conjecture is that you obtain a theory in 6 dimensions on a finite dimensional torus. Now, following the advances that I have discussed before, by now we have a lot of examples of these cross-dimensional dualities exactly of this type. You start from some, say, 1,0 6-dimensional theory, and we understand what the compactification on a torus with punctures gives us. Again, these are some quiver theories. So a question one can ask whether all six-dimensional CFTs can be, in a sense, deconstructed starting from four-dimensional ones. So can one come up with a classification program of six-dimensional CFTs by studying, for example, directly four-dimensional Lagrangian theories? Okay, so this is a bolder question one can ask. Okay, starting from four dimensions, is everything obtainable? I mean, we can obtain maybe some lower dimensional theories, some in four-dimensional theories, but can everything be obtainable in some types of limiting procedures starting from four dimensions? So before finishing, let me make some additional comments. So again, the whole philosophy of this talk was that dimension doesn't matter. There is a lot of things that we can deduce about quantum field theories if we give up ordering things according to dimensions. And in that respect, of course, there is nothing special in this four-dimensional boundary that we have chosen. So one can go to lower dimensions. For example, one can study a cross-dimensional duality starting from 6 dimensions and going to 3 dimensions. Again, this is something that was discussed already a long time ago, and some interesting works appeared also in recent years. For example, trying to engineer topological phases in 3 dimensions starting from 6 dimensions. One can start from 5-dimensional CFTs. Nothing is holy about 6 dimensions, and try to place them on a Riemann surface and obtain CFTs in 3 dimensions. So this type of research in its infancy. Another thing that I mentioned is that a lot of interesting special physics of in lower dimensions, for example, mirror symmetry in 3 dimensions, can be lifted to 4 dimensions. There is no mirror symmetry in 4 dimensions, but there are some theories and some properties that one can discuss in 4 dimensions, limits of which to 3 dimensions become mirror symmetry. There are other very interesting questions. Of course, all of what we have discussed was about skeletal properties of supersymmetric theories and supersymmetric skeletal properties. What about going beyond skeletons? Okay, this is a major question in this field. Another question I would say is connecting with Bootstrap. The philosophy here was based on relations between different theories. The Bootstrap approach mainly focuses on a given theory and the properties of those theories, so I think there is a lot of room to marrying these two approaches. Of course, another interesting question is whether non-supersymmetric interacting quantum field theories, conformal field theories, exist at all in dimensions bigger than 4. What about non-supersymmetric quantum field theories in general number dimensions? Do all of them come from deformations of supersymmetric ones? And some aspects of this will be discussed in a talk by Emily Nardoni. So another question that we can ask is, does all physics, all quantum field theoretic physics come from theories with 8 supercharges, which is a minimal amount of supercharges in 6 dimensions? 8 supercharges is something we like, and the question is, well, is everything reducible from this type of physics? So let me summarize by stating these things. So higher dimensional SQFTs are an extremely rich, in a sense, experimental laboratory to study theoretical ideas in QFT. It is experimental because this laboratory is intrinsically interacting, so we need to come up with, just perform various computations that we can and try to deduce what we can from these computations. And another main point is that the CFTs, SCFTs in all dimensions are intimately interrelated. So thank you very much for your attention.
Thank you very much for this beautiful review. Other questions? Well, I can start with the question. Do you have any extra comment about the destiny of non-local operators like defects or Wilson loops, Wilson lines through, dimensional?
Yeah, I think there is I believe there are some works addressing them, but it's really something that needs to be. The main focus was on local operators till now, and only now with this advent of these higher structures, there is interest in them. There are a lot of understanding coming from more string theoretic and geometric perspective, but from the angle I was presenting, like purely field theoretic, of course, people studied these objects directly in field theories, but not as much in this slide.
Okay, thanks. Another little question. When you talk about compactification, you may also have twisted compactifications, right?
That all of these compactification are, in a sense, we preserve, as I mentioned on the first slide, we preserve supersymmetry. So that's that was the only thing we discussed. So all of them are twisted in some sense.
Any other question? Yes, there is a question there.
Just a comment about this across-dimension IR duality, and there's a you mentioned that should be referred to string theory, but there's a little string in between the full-fledged string and SCFT, and little string theory, of course, have this T duality because it is little string, and that I think that is some mother version of this, and
that's right. That's another way to generalize this type of questions, right?
Yeah, just comment. Thanks.
Any other question? We have still some time.
Yeah, I wanted to ask, because you were very definitive about the statement there is no Lagrangian in 6D, and while it's
so
quite
the
clear
statement
for the
is
2,0 theory, because you don't have a free parameter. I wonder if you have an argument for the 1,0 theories, why there should be that.
So the only thing I'm claiming that there is nothing you can write with usual types of Lagrangians which preserve Poincare symmetry. Okay, so with usual fields and interactions, without any extra gadgets, you cannot write Lagrangians which flow to these SCFTs.
Okay. Any other question? If not, let's thank Shlomo again.